Hello everyone. Thank you for joining us. I am Amaan Syed and with me are Rikhav Satra and Prabhat Patni. Today we'll be presenting insights from a research paper titled Performance Evaluation of Serverless Edge Computing for Machine Learning Applications. This paper explores how combining edge computing with serverless or function as a service can enable ML applications to run closer to data sources, and it provides a detailed performance evaluation on this approach. Moving on to the next slide.
So imagine you're sending a letter to your friend who lives in the same city. If you mail it through a post office in another country, it will take much longer to reach your friend than if you just handed it to them directly. So this is similar to how traditional cloud computing works for smart devices. Data from things like sensors or cameras has to travel all the way to a distant cloud server and then back, which causes the delay. Now think of edge computing as setting up a mini post office right in your neighborhood. The data doesn't have to travel far, so it gets processed much faster. This is especially important for things that need quick responses, like self-driving cars or smart traffic lights. So serverless computing is like having a magic helper who appears only when you need them, so and disappears when you're done. No need to hire someone full time. It makes running applications easier because you don't have to worry about managing servers. So the big question is, can we combine the magic of serverless computing and the speed of edge computing so that even small local devices can run powerful applications quickly and easily? This research paper explores whether technology, which was designed for big cloud data centers, can work well on smaller local edge devices without slowing things down.
So, in the problem statement, as the problem statement explained by Rikha, running an ML machine learning on edge devices poses significant challenges. There is no standard scalable way to deploy ML models across heterogeneous edge nodes. Typically, engineers have to use ad hoc manual setups that requires deep expertise in both ML and hardware. In contrast, the cloud that has embraced mature serverless platforms. However, it remains unclear how well these cloud-based serverless frameworks perform when deployed at the edge. The paper addresses this gap by evaluating the performance in the term of latency, scaling, and more of several serverless frameworks on edge hardware, as well as comparing how different ML models such as CNNs or versus LSTMs perform in this environment. Essentially, the paper asks, is serverless computing a viable model for deploying ML at the edge? And what are the associated performance trade-offs and the best practices?
Let's go over the objectives. To tackle the problem as explained by Prabhat, the paper sets out a few clear objectives. We have to evaluate four open source serverless frameworks, namely Kubeless, OpenFaaS, Fission, and FunkX. Then we have to test the framework under real machine learning workloads. The researchers use a simple hello world function as a baseline and then evaluate two ML interface tasks, one using a convolutional neural network CNN and another an LSTM, long short term memory, to simulate real world scenarios. Then we analyze key performance metrics, response times under various loads, auto scaling behavior, performance differences between the two programming languages, namely Node.js and Python, and even feasibility considerations for training ML models on the edge are examined. These objectives align with the paper's contribution, ensure a comprehensive analysis of latency, scalability, both interference and training performance at the edge.
So the experimental setup was designed to realistically emulate an edge computing environment. The test bed consisted of four Raspberry Pi 4 devices, each with a 1.5 gigahertz ARM quad core CPU and 4 GB RAM, connected over a local Wi-Fi network. A laptop running Micro K8s acted as a Kubernetes master node and also generated the test workload. Each of the four serverless frameworks, Kubeless, OpenFaaS, Fission, and FunkX, was deployed on the Raspberry Pi cluster, which with each framework isolated in its own Kubernetes namespace to ensure fair comparison. Apache JMeter was used to generate HTTP requests, triggering serverless functions to the Pis. The workloads included a simple hello world function and two machine learning interface tasks, one using a neural network, CNN, and another using an LSTM model. These models were pre-trained offline and deployed as a serverless functions for inference. Model files and input data were stored in a local AWS S3 compatible storage, allowing the PIs to fetch resources efficiently. The Kubernetes managed the orchestration and auto scaling of the serverless functions. For the Kubernetes based frameworks, a horizontal pod autoscaler was set to maintain 50% CPU utilization, dynamically launching additional pods as needed. FunkX used its own endpoint based scaling mechanism. In summary, this architecture provided a controlled, realistic environment to benchmark serverless frameworks for machine learning at the edge, focusing on latency, scalability, and resource efficiency.
So, before we discuss the experimental results, let's briefly introduce the four serverless platforms evaluated in the paper. The architectural designs differ significantly. OpenFast is this is an open source fast framework network that leverages Docker and Kubernetes developers who supply function code, which is then packaged into containers. OpenFast includes a gateway for receiving requests and a watchdog to invoke the function, with auto scaling based on the request throughout the Prometheus metrics. Kubeless, a Kubernetes native serverless framework that treats functions as custom Kubernetes objects. Kubeless benefits directly from Kubernetes' robust scaling, networking, and management capabilities. Fission, also built on Kubernetes. Fission emphasizes rapid function startup time and maintaining a pool of warm containers to lower latency. It uses specialized routers router components for directing requests and auto scales based on the CPU usage. However, the paper notes that Fission's router can become a bottleneck under high load. Punkex, a newer federated serverless framework developed for distributed and scientific computing. Punkex operates without Kubernetes by using its own endpoint system and requires communication with a cloud hosted service, which has introduced additional overheads. Each framework differs in design choices, whether it's integration with Kubernetes or reliance on coordinators, and each play a key role in their performance characteristics, especially regarding latency and scalability.
Let's go over the experimental setup. How did the researchers evaluate these frameworks? The study measured response time as the primary performance metric under various conditions. Using Apache JMeter, the experiments involved generating 1,000 HTTP requests per test case while varying the number of concurrent clients 1, 5, 10, 15, and 20 to simulate increasing load. Each experiment was repeated multiple times to ensure that the results were stable and reliable. In addition to response times, the study also tracked the success rate of the requests uh, and the number of containers pods spawned under load as an indicator of each framework's auto scaling behavior. The workloads tested included a hello world function, a trivial function implemented in both Node.js and Python serving as a baseline for latency. CNN inference, a one-dimensional convolutional neural network model processing segments of time series data from the HAR dataset, simulating IoT data analytics. LSTM inference, a long short-term memory model used for sequential prediction tasks, providing a more computationally intensive challenge. For auto-scaling, Kubernetes-based frameworks Kubeless, OpenFast, and Fission were configured with a horizontal pod autoscaler set at 50% CPU utilization. Each test began with a single pod. Additional pods would be launched if CPU usage exceeded the threshold. Although FunkX uses a different scaling mechanism, similar principles were observed. This setup allowed the researchers to analyze both the static and dynamic behavior of these frameworks under varying loads.
The research paper's response time results reveal several interesting trends. With the Hello World and ML inference functions, Kubeless consistently demonstrated the lowest latency, typically in the range of 10 to 50 milliseconds, owing to its close integration with Kubernetes. A notable observation was the performance difference between languages. Node.js functions outperformed Python functions significantly. For instance, if in OpenFast, the Node.js version of Hello World was nearly 19 times faster on average compared to its Python counterpart. Kubeless also showed about 10 times faster response with Node.js compared to Python. The only exception was Fission, which performed similarly in both the runtimes. Additionally, as concurrency increased, Fission experienced higher and more inconsistent latencies, likely due to its router component becoming a bottleneck. In contrast, while FunkX had a higher base latency, primarily because each request first communicates with a central cloud service, its response times scaled more gracefully under increased load. Overall, for simple workloads, Kubeless and OpenFast delivered the most stable and efficient response times, according to the paper.
So, the paper further examined how autoscaling impacts performance, particularly for the ML interference workloads, CNN and LSTM. Uh, Experiments were run into the two modes, with autoscaling enabled, allowing multiple pods, and with autoscaling disabled, a fixed single pod per device. For CNN workload, Kubeless again excelled, achieving optimal response times in both autoscaled and non-autoscaled scenarios. Interestingly, Vision displayed the most significant gains for autoscaling, with autoscaling enabled, and its response time improved by about 27% for a single concurrent user, uh, and nearly two times faster for five users compared to running on a single pod. For the heavier LSTM workload, both Fission and FunkX benefited from autoscaling, with Fission showing improvements of approximately 5% at the low load and up to 30% at the higher load. In contrast, tubeless and OpenFast showed smaller performance differences between autoscale and fixed setups, indicating that in some cases, a single pod might be sufficient, or the autoscaling overhead offsets the benefits. Notably, the paper also reports in certain configurations, autoscaling, if properly constrained, could even slightly harm performance in platforms like OpenFast.
Now let's go over the training results. Beyond inference, the paper also investigated the feasibility of training ML models on the edge. In a separate experiment, the researchers compared the training times of CNN and LSTM models on a Raspberry Pi against those on a standard x86 laptop. As expected, training on a low powered device was significantly lower. Specifically, training one epoch for the CNN model on a Raspberry Pi took about 15.6 times longer than on a laptop, while for the LSTM it was roughly 7.4 times longer. Although the CNN achieved higher final accuracy, it also demanded much more time to train on the Pi. In contrast, during inference, the CNN ran faster due to its parallel friendly computations, while the sequential nature of the LSTM led to slower performance. The key takeaway from the study is while serverless edge computing shows promise from model inference, training complex models on such resource constrained devices remains impractical.
So, to wrap up, let's think of serverless edge computing as building a team of smart local helpers who can quickly solve problems without always calling a distant headquarters. The research shows that Kubeless is like the star student, fast and reliable in most tasks. Fission can get overwhelmed when too many requests come in at once, but it improves a lot if you let it add more helpers. That is auto scaling. The language that you use also matters. Node.js is like giving clear, simple instructions, while Python can slow things down. Auto scaling, adding more helpers when things get busy, can help, but if not managed carefully, it might even slow things down in some cases. And not all tasks are suitable for these local helpers. Simple, quick jobs work at best, but heavy training tasks are still better left to big cloud servers. The main takeaway is that serverless computing can work at the edge, but if you have to pick the right tools and settings for the job. Future improvements could make these helpers even smarter and more efficient, especially for resource limited environments. Thank you.